I think we are now coming to the more interesting part of the lecture. So, first of all, I will discuss some Lie algebra structures. And also, more importantly for us, Poisson algebra structures. You will see what I mean. And we'll talk about constants of motion. Hamiltonian systems. And we'll talk about the notion and some details of completely integrable systems. These are topics, standard topics in classical mechanics. So, for all of this, we have the basic exact sequence. Of a symplectic manifold. Namely, constant functions, manifolds connected, smooth functions, and let me just use a physics word here. These functions are called observables in classical mechanics. And associated to observables, we have Hamiltonian fields. We talked about that in great detail. This map sends a function, let me say a Hamiltonian to make it H, to the associated field X at H. And if we have such a Hamiltonian field, we have a contraction mapping here which sends the Hamiltonian field to the Durand class of the contraction in the first Durand cohomology. And that's exact. I call this middle map F. The word field is associated observable to a field, and this I denote by contraction that associates field to a contracted form and then really just the Durand. Okay, that's the basic thing to look at. And it turns out it's very fundamental, and every physicist knows this in an ad hoc way, but maybe not systematically. This is an exact sequence of Lie algebras. Fundamental Lie algebra structure on everything here, in some cases rather stupid. Let me just recall what a Lie algebra is. Lie algebra, let's say G is a Lie algebra, means that it's equipped with a bilinear pairing. So it's a vector space. In this case, we will be dealing with this object, which is an infinite, but certainly infinite dimensional. This is infinite dimensional. In most cases, this is finite dimensional, and of course, this is just one dimensional. So here we allow infinite dimensions because, particularly because the most interesting things here are infinite dimensional. So this is a vector space, in this case over the real numbers. So with a bilinear pairing that's antisymmetric, symmetric. So you can see already, given that we're in the symplectic setting, that we're coming close to symplectic geometry just with the Lie algebra. And plus the Jacobi identity, let me just write it again so that you know, this is just a review, just to remind you where we are, that this operation is a derivation. And that's really the way to think about it. You think about this thing operating, so you think about the Lie algebra operating on itself by this, and that means that if you operate on a product in the sense of this Lie algebra, it's the same thing as operating on the first thing times the second, and then operating on the second thing times the first. So that's what a Lie algebra is. These things occur all over mathematics, and in particular in physics, and in particular in classical mechanics, in particular here. So the first Lie algebra that we know about, I'm just going to comment on, is the vector fields together with bracket here form a Lie algebra. So I have to tell you what the bracket is. So this is a standard Lie algebra on any manifold. And the bracket, of course, we've talked about this in great detail, but let me just write it again. Xy minus yx, and as I think some of you said, it's not so obvious that, I mean, you could write down x, y, and yx, but a priori these things are second order differential operators. You differentiate twice here, but actually the second order term gets killed here, and it really is a first order derivation. I think a beautiful comment along those lines is this, that actually well, we can write down something, namely Lie x, Lie y. And we've had this big discussion, where does Lie work? I mean, Lie works anywhere you want, right? It's just, you differentiate anything you want. And you look at this operation, this is really the operation somehow. This is the bracket of a linear operator, and you can check that this is exactly the xy. And you can see very easily here at the level of functions that this thing's a derivation. So let me just do that for fun. We're now even at the beginning of the lecture having fun. This shadow here is not too good. So what I can do is be, my last Willeke lectures, be a little bit pedagogical. Let's see here. Lie x, Lie y, minus Lie y, Lie x, applied to f times h. Okay, now let's see if I can get this. This is Lie x. Now I'm going to put it in here. Lie y, so that's it's f Lie y of h minus a plus h Lie y of f. Right? And then I have to, just for fun, we're going to see how the second order term gets killed here. This is then Lie y of Lie x. The product is for fun here, so how would I do it? So f Lie x h plus H V X Y of F. And then we just continue having so much fun. Let's see what happens here. This is going to be terrible, right? I should have never done this. So let's see here. This is a product again. So this is the X of F times the Y of H plus F Vx of Vy of H. That's the first term. Second term is the X of H times the X of H, the Y of F, and then plus, what do we have here? We're operating here, so this is H, the X, Y of F. And now I should be intelligent enough to exchange Y for X and subtract. Right? Because all I did over here was have exchange Y for X, so minus all of this junk here, minus I exchange Y for X, X and Y. This is like waking up early in the morning and you haven't even had a shower, so you have to do something like this. So if you change Y for X, this gets changed, but we see that what we have here is exactly the change, so that means that this cancels, and we are left with, this is a symmetric term, so as you see, oh, now I made a mistake. Huh? And now I have to subtract, right, and now I have to subtract these terms with having exchanged X and Y. Right. So this is F. Now you see, now I have to subtract. How I have to do this? So I have to exchange X and Y times H, and then this term plus H, and then exchange X for Y. So that shows you it's a derivation. Right.
Professor, how could you change X and Y?
You change it in the sense of symbols. So when you do a calculation, you try to minimize working with the hand. And so you see here, if you see here, this term here is the same as this term, except I have to put X here and Y here. Yeah. Okay. So I just said exchange X and Y in the first term and subtract. And now I look at things that are symmetric and anti-symmetric and so on, I just cancel. So that's all I did in my head. Right? Just proving the fact that the best mathematicians are the laziest. So I'm not only lazy, but I'm also bad at calculation, but nevertheless I actually got it right. So you see, this is derivation. F times the derived thing of H times the derived thing of F. And that's really sort of, I think, a nice way to look at this trivial statement. Okay. So that is a Lie algebra. And now a little proposition. Is that and this is an important proposition, the Hamiltonian fields, you see the Hamiltonian fields are contained in the full vector space of vector fields, so this is a Lie subalgebra. Of the vector fields. This is fundamental. You take one Hamiltonian field, another, you bracket it, it's still a Hamiltonian field. It should be. Yeah. And the reason it is very simple. Let's just prove it. Is the bracket, as we know from above, is this as an operator. And if you apply it to a Hamiltonian, it is 0, because by definition it's a Hamiltonian, and a Hamiltonian is a Hamiltonian if and only if it's annihilated by a Hamiltonian. Well, okay. Oh, what am I doing? I'm sorry. Stop, 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 stop. Recall the definition of a Hamiltonian field is that it is locally, doesn't change, the one parameter group doesn't change the symplectic form. That means it's a local isometry of the symplectic form. That's the statement that the Lie derivative, that's the definition of Hamiltonian. Let me just write it here because you've forgotten. This means that if something is here, it means that the Lie derivative kills the symplectic structure. It means it's an infinitesimal isometry of the symplectic structure, and so obviously this bracket kills the symplectic structure because Lx kills it and Ly kills it, therefore the bracket kills it. Okay. That's it. Okay, so that's a good proposition. So that's the first step in discussing the fact that this is an exact sequence of Lie algebras. Here we have the Hamiltonian space, just the usual bracket. Here is the correct Lie algebra structure. It is the Lie subalgebra. If you bracket two fields, you stay in the Hamiltonians. Maybe not so obvious. The Lie algebra structure here is trivial. So this means, just stupidly, A bracket B is 0 for all A and B. And this is one-dimensional and therefore automatically trivial. So A bracket B is 0. So these, I've defined the Lie algebra structure on all but one thing in this sequence. And the stupid structure here, the obvious structure here because it's a subalgebra of the vector fields, and finally the trivial structure here. So the main point is the Lie algebra structure on the functions. The Lie algebra structure on the functions. This bracket is called the Poisson bracket. Poisson is not a fish. It's a human being. But nevertheless, a French human being. So let me do this here. It's a very interesting structure. I think this was understood by Lagrange, and this is certainly the time of this kind of mathematics, the beginning of the 19th century, time of mathematics. So I will define the Poisson bracket. So this is the symbol is this. Every physicist has seen this symbol, but not all have really looked closely at the situation, and I think it's really good to look closely at it. So if you're in physics, I recommend you look closely at this. So I'm going to define it. It's a very interesting definition. So I have to take the bracket of two functions. It's interesting, right? Well, there's one obvious definition, and it works. And I'm always worried that I've gotten the sign wrong, but this morning when I was trying to wake up, I checked the sign here, and I think that's the right sign. So it's either plus or minus that. In this business, it's really difficult to get the sign right. But I think actually somehow normalizing the sign here, it normalizes the sign in the entire discussion. So let's hope that this is the good sign. This is really a beautiful definition. Look at this. You see, let's think about these things as vectors at a point. So this is x, f at a point in the manifold. Say even in some simple situation, standard space. This is x, h, and this is the positive oriented thing. This is really the normalization, and the Poisson bracket is the area between those two vectors, right? That is the area. You see, that is the area form. If you do this in the standard structure, that's the determinant of these two vectors in two dimensions. So it's really what we're discussing here is the Poisson bracket at this point. So it's very interesting. Yeah? You have these two vector fields running around on your manifold, and you take this bracket, which is just the symplectic form, and you're measuring somehow as they run around the variation of this area. It's fascinating, right? Okay. Well, we know actually, at least implicitly, and I think explicitly, we know what this thing is in terms of a differential operator. So, you know, every physicist thinks of this thing as a differential operator. So, we think of this thing, f point, as a first order differential operator. And let's see what that is. So as an operator, so we apply it, f point of h is equal to this thing applied to this vector field h. But don't forget what that thing is. That means that's df, because don't forget, let me just write this. df is contraction of xf with omega, so that's just df applied to xh to xh, which is equal to xh of f. That's nice, but if you turn it around, because you want to think of that as an operator, f being an operator, this is minus xf applied to h. Right, and I just reverse the variable. So that, let me just write it here. This as a differential operator is just minus xf. So it's the same, it's basically the Hamiltonian field, except there's a minus sign. I think that's correct, actually. There's a minus sign. So you think of this as the Hamiltonian field. Okay. Now, we can have some fun. You know, that kind of fun. We will now have fun. You see, physicists love to do calculations, right? Yes. Mathematicians love to avoid calculating by thinking. But, unfortunately, there's a point. Every mathematician privately calculates all the time. At least I do. You should see my papers, number of wrong calculations. Yes. But then at the end, I understand something, and then I throw it away because I don't need the calculation. Right? But today we have to do some calculations where we actually need it. So one of my first goal here is, maybe one of the first goals today, is to prove that smooth functions equipped with the Poisson bracket as above is what we call a Poisson algebra. I haven't told you what that is, but let me just, the Poisson algebra. So I have to tell you what that is. And the calculation will probably take up this blackboard here. And I will prove to you that I have calculated. Also, even before breakfast. So, but I need to tell you what is a Poisson algebra. So let me do this here and save this blackboard for calculation. So Poisson algebra is this. Please notice that there's another operation. Notice this thing. You see, one beautiful thing about algebra is that it forces you to look at underlying structures that you might normally be blind to. And once you look at them, you say, that's pretty stupid. But it makes you look at them. So you see this thing here is an associative algebra. Namely, you can multiply two functions. It's even commutative, right? All sorts of things are good. So this is really a simple-minded thing. And so furthermore, this operation, and I'll tell you, a lot of physicists think of this operation as multiplication. This F times H. You think of F acting on H. You're hitting H from the left by an operation. This operation is this bracket. So there are two multiplications here. The Poisson, the bracket operation is multiplying a function by F by this bracket, and then the stupid operation, F times H. Right? And by thinking about algebra, you realize that maybe you should think a little better what's going on here. And the Leibniz rule is in the easy to check. I won't check it. It's really easy to check. It's obvious to check in some sense. F times GH. See? Okay, so I'm multiplying here, and you see, this is the compatibility of the two operations. The bracket operation and the associative algebra operation. And the rule is, of course, a Leibniz rule, right? So what is that? That's F, that's, for example, G, F, H, plus H, F, G. And that's trivial to check because that thing, we know that this operation, this is trivial because this operation is just the first order linear differential operator. So this is easy to check. It's just the Leibniz rule of that operation. And F applied to the product is G, F, H, H, G, N. So that's that operation. So there are two operations on this Poisson algebra. This is the Leibniz rule and then the Jacobian. So it looks like we're German chauvinists. Leibniz, of course, as you know, very early in the history of mathematics, but Jacobian much later, and really realized, I think, these kind of phenomena in such contexts. And the Jacobian rule is, well, I've written it out. I'm getting sick and tired of writing it. So it's F G H equals F G H plus G F H. Well, two derivation rules. One derivation rule, in some stupid way, multiplication with respect to the associative algebra structure, and the other derivation rule, multiplication with respect to the Poisson bracket. And such an algebra is called a Poisson algebra. So here as an example, and you can imagine the general definition. These two these two things have to be satisfied. You have an associative algebra where these two things are satisfied. Okay. These things are fundamental in mathematical physics. And the first Poisson algebra is this thing. So we need, the goal is to show this. We must show that the Jacobi identity is satisfied. And you will see the proof, and I hope you like it in terms of conceptual background of the proof. The technical points you will probably hate, but the conceptual background is this is absolutely equivalent to the fact that the symplectic form is closed. It's 100% equivalent to the fact the symplectic form is closed. All over the place we've used the symplectic form being non-degenerate. And now you will really see in a very strong way that this is equivalent to the symplectic form being closed. Okay. Fine. Now to prove this, we even prove an elementary but basic lemma. And this is, I'm going to do some calculations for this lemma. Is the following basic lemma. Of course, this subject is now old, so the notation is now perfect, you see. So, well, old means I don't know how long, but guess what? That's beautiful, right? That the Hamiltonian of a Poisson bracket is the Lie bracket of the Hamiltonian. Right? It couldn't be better. Now that's more than notation, because this means that the mapping, which I'll write it here in a formal way, which sends functions to fields. So Hamiltonian, this mapping which sends functions to fields preserves the bracket. All right? It says, right? That's what it says. Look. The field of a bracket is the bracket of a field. All right? That will say then, you see what my goal was. Remember, my goal is right here, is to show that this is a Lie algebra, and we have to do some work to show that. But once we show that this is a Lie algebra, this lemma, which by the way is used in showing that it's a Lie algebra, this lemma shows that this is a Lie algebra mapping. Right? Right? The bracket of two functions goes to the bracket of their fields. So this is a key lemma. Let me prove it. Okay? So I really have to compute. So are you ready? So D, I have to compute. So I have to start with one of these things. I'm going to use H instead of G. D of F and H. So let me write here to show what we have to show. Right? What I have to show is, remember, D of a Hamiltonian should be the contraction of the symplectic form with the fields. So I have to compute that and see if it's that. Okay? Right? I hope, I don't know how good you are at mathematics. I don't know you well enough yet. But I hope, no, seriously. You see, conceptually you get this thing set up. This is the artwork here. This is the work of a composer, of Beethoven. to set this thing up and really see the structure, and you see the structure. For example, Michelangelo, I don't know if you know the sculptor, Michelangelo. So, yeah, you will, it's very interesting, Michelangelo. So he didn't finish many, so have you been to Roma, and you've seen this wonderful, it says Pietà, with the dead Jesus on the lap of you see, you're a Muslim, so you don't care. So you go in the great Basilica of the Vatican on the right-hand side, you go there and everybody gets to look at this beautiful thing. It's in white marble, and the mother of Jesus is and just the curves, the geometry, it's incredible. It's the suffering, the beauty, it's incredible. It's just incredible. Then you go to Florence, and you go to the Accademia Museum, where there are many, many things, including his famous David. Have you seen this famous David of Michelangelo? And you, as a mathematician, you're very interested because he made it to look at this thing. It's huge. And then if you look at it up close, everything is wrong in terms of the dimensions, because he's assuming you're looking at it as, you see what I mean? Maybe the hands are too big, or everything's out of proportion. But if you look at the right distance, it's gorgeous, it's perfect, it's ingenious, it's set up beautifully. And in the Accademia, there are many things that are unfinished of Michelangelo. So they're called his prisoners, and they're coming out of stone at you, unfinished. The entire structure is set up, the entire culture is set up. He really didn't finish any of his works. Do you understand? He had assistants who smoothed all these things. These people have to be great sculptors, of course, also. They are his students. My doctoral students are also great future mathematicians. No, I'm not a Michelangelo. So, but anyway, to set this thing up, I think is brilliant. To set this thing up in this way, with seeing these Lie algebra structures, I think it's a brilliant, I think it's a contribution. Anybody can prove, if you're given this, I mean anybody in this room, except for making sign mistakes, given something to prove this, anybody can do it, okay? Anybody can do it. I'm going to do it now to prove that anybody can do it, okay? But keep in mind, what is the real artwork in mathematics, and what is stuff that anybody can do. And keep in mind, if you're going to be a mathematician, that you should do the artwork. You should also do the computation, but you should focus on the artwork. Okay? You should not focus on the integral of e to the x. You should not focus on the integral of y1 degree. You should focus on the artwork, right? The technical stuff you must know and command, but you should focus on the artwork. Yes? Okay. D of f h equals d of x h of f okay, equals d of ddt of gxh of t, okay, of f, okay, f pulled back. Now this is a little bit of artwork, because you see, you should understand, one, if you have a vector field, the only way to do anything with a vector field is the local one-parameter group. I've told you that 100 times, right? So you see, I put it in there. I put it in there. The second thing is, you shouldn't just write down composition with respect, you see, of course, all this is f composed with this function. This is the way you pull back functions. But you should not put it in there and confuse the matter. You should isolate the structure as you're doing it, right? And pull back commutes with d. So d of something pulled back is pulled back of something. So, well, I promised I was going to get it in here and I lied. So, okay, well, let's see. Just for fun, I'll erase this so we can have some didactical fun. Yeah, I wish I had assistants like Michelangelo. Okay, so let's see what we can do. I'm gonna bring that that pullback outside, but I want to have some room for it here. Okay, so let's call this dagger. So dagger equals, now I'll put the pullback outside and you can check that it doesn't matter what this DDT, that's just the difference quotient derived. And so you have pullback XH, actually you're pulling back the map here of DF. DF is equal, now we use what DF is. You see, anybody can do this, as long as you follow your nose. And DF, so it's XF of this one form. That's what DF is, because DF is Hamiltonian. It's Hamiltonian, isn't it? Now, I don't know about you, when I have a big calculation, like, to me this is a big calculation. For you, probably it's nothing, it's a joke. I mean, physics, they calculate for an hour and 15 minutes, and then that was the lecture, and then the next lecture they write on the blackboard on the left-hand side, equals. Yeah, I calculate a few terms and I'm getting extremely tired. Yeah. So, but I don't know about you, I feel that what we should do in such a calculation is I try to isolate what we have seen here, and what the devil have we seen? We have seen here, so I'll put it, I like to put it in a box. D of F H equals ddt, t equals 0, gx h of t, pull back, omega, x, f. That's what we've noticed, right? I like to do it like that, except I don't know how to do that in tech. I tech all the time, as you know, because I send you files, but there must be a trivial way to make a nice box without anything. Is there a command? Yes. Box or something like that?
Yes, it's slash box.
Slash box. you just put slash box at the beginning and end begin slash box and end slash box? No, just slash box and bracket and bracket.
Yeah.
Okay. Okay.
I'm not sure.
All right, Mihai, the next lecture notes are going to be boxes all over the place. Yeah, I've always wondered how to do that. That's nice. So what that means is, now I select some absurd symbol that's far away from this. In this case, I think y is not bad. Is equal to ddt t equals 0 of this thing. Oh, I should have been smarter than this. Oh well. Oh no, I'll be smart. Let's see what happens. Y. So this is the pullback of this differential form applied to y. So that is the pullback ddt equals 0. I hope I get this right now. Of this differential form applied to y. So omega of xf. This. So the pullback of a differential form is the push forward of the vector field. Okay. 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 Ha ha ha. Don't forget that this operation is an isometry. So this is the same thing as and now I'm going to be really tested. So this is pull back. Inverse of x, y. Okay. If I had been smart, which I am not, I would have had that ddt inside, but that's linear, so that's a trivial point. So it's omega ddt this thing and now, of course, what this is the Lie derivative of the field x, but the inverse Lie derivative of the field x, of the field xf with respect to the field f x h. Remember, the Lie derivative acts everywhere you want. It acts on fields by push forward and derivative, so you get the Lie derivative, but it's a inverse, so it's the inverse Lie derivative of that. And of course, you check what Lie derivatives do, and this is the thing that I hate, but of course it gives the right sign. The Lie derivative with respect to x of y is minus the Lie derivative of xy. So this is, well, what did I say? It's minus, I should put minus x h x f, and that's x f x h.
But the minus 1 doesn't count?
Huh?
What is the inverse Lie derivative?
Yeah, let's be careful. You're absolutely right. So, okay, so, so we have the inverse here for sure. Okay. So that is the same as putting minus here. So that's minus and minus is a plus. That's what you're saying, right?
No, I don't understand what inverse Lie derivative is.
Huh? You don't know what inverse does. That changes the direction of the flow. So that's, right? So that changes the direction of the vector field, right? So I'm seeing that I probably made a sign mistake at the beginning. So yeah, this is good education. Let's see. So wait a minute. We get all the way to the end and everything's great. And let me erase this and be very slow about this to make sure the sign is right. What I know, and I've checked 100 times, and you can easily check me on this, is the Lie derivative. This is a Lie derivative here, but okay. So this is here for sure the Lie derivative, because it's the inverse. It's the same thing as no inverse and putting a minus sign down here. So it's the Lie derivative of xf with respect to minus xh. And what is true for sure is the Lie derivative of x derivative of y is minus xy. So this is therefore minus the minus is a plus. This is xh xf. And now I'm going to change every sign in the lecture. Right? All right, so what I have here is at the end of the day, I have in the box now that I'm going to put in the lecture notes, that d f h of y equals all of this stuff equals omega of this thing, x, h, f, y. And if I keep the signs, this says that x of Poisson bracket fh equals, you see it's the wrong, it equals contraction, it equals minus, because it's the right direction, xf, xh. You see? And you want this thing to be the right sign. You don't like this minus sign, right? You understand what I'm saying?
But why do we define the derivative with minus? Last time I think we said the derivative.
It's not a, okay, so I see what you're saying. Yeah, I could define the derivative with plus. Yeah?
Mm-hmm.
But everybody in the world defines the derivative. So, no, Elisa, look, the derivative, this thing, this is not a definition, this is a theorem. And this thing is by definition, it's a question of how you do it. It's the derivative of the push forward, it's this definition. And that seems to be the right definition here. And everybody uses this definition. Yeah? And you see, push forward is covariant. So I like to have this as an action. But in the back of this thing, something I don't like, but everybody does it, is the Lie derivative of a form. Everybody does it this way. At least in this symplectic business, is everybody does it in this way. Right? That is from the point of view of structural mathematics wrong, because pullback is contravariant. Do you understand what I'm saying? If you compose two things, it changes the order. Pullback. Push forward, composing two things remains the order. So you to get the order right, you should pull back with the inverse. And then it's covariant, and then you have the right sign on everything here. But nobody does that. Okay? So now I have to change the bloody sign. So, but the one thing I like about changing the sign, this makes me happier than ever. This is the first time, even after breakfast I couldn't do this, is now minus, right? And now everybody is happy about this, that the differential operator has no stupid sign.
Why? This is true.
And now this theorem is true.
But you computed its minus sign.
Yeah, so you change
Change the definition.
Okay,
No, what do you
change
mean?
everything. Okay.
I computed everything correctly till the end, and I said I hate the sign at the end.
So you change everything.
Yeah, no, I mean that's reasonable, right? Okay, so now everything's good.
Why
So-
don't you change the theorem?
Huh?
Why don't you change the theorem?
What do you mean change the theorem?
You can change the lemma to with the minus sign.
Okay, I can change the theorem. That's a very good. Why don't you change the theorem? Because I want the Hamiltonian field of a bracket to be the bracket of a Hamiltonian field. I want this morphism to be a Lie algebra morphism. And you see that somehow fixes the sign. Right? Because when I went through this whole calculation, I did it wrong and I had a minus sign. You see what I'm saying? I don't like that. Of course, as you say, I could change it, I could change it all to get the signs right. But okay, now I think this is fixed now. Okay. All right, so that's the basic lemma. Okay. We're not finished with the big data calculations yet. Because I've not yet proved the Jacobi identity. So let me recall what I have to prove here at the end of today's lecture. The Jacobi identity, but let me formulate it. So now the Jacobi identity. Oh, it's just FG GH equals FG H plus G. Now, as I said, this is equivalent to, I'll repeat what I said, this is equivalent to B omega equals 0. And for this, I will make everybody happy with another formula. So, this formula, I think, this formula I'm going to write on the board, it was actually pointed out by Cartan or Lichnerowicz. This is typical of French, good French mathematics. They really isolate important quantities and ideas. This is a formula for V and this is another way. We've had a big discussion in this class. Remember, one definition of D is just remember, you just define in local coordinates d of f times dx I as simply df wedge dxi, and then that's the definition, but of course it's nonsense because it's not well defined independent of coordinates. And that's the reason I chose this other definition. It's abstractly well defined. And one other way of showing that this definition is independent of coordinates is to write it down as a formula. And I think this is what Lichnerowicz did. This is related to a topic called Lie algebra cohomology. So that's, you can tell your mother about that. This is related to something like Lie algebra cohomology. So I'm now going to write down d of omega. Okay? Okay. Here we go. D of omega. Okay. Applied. Now I usually start with 0. I don't know why, because I've gone up 1. If I start with a K form, I need to get a k plus 1 form, and so I somehow or another, in my formulas, always start with 0 on it. I don't know why I do that. Okay. This is the sum over I, all possible i's here, of xi applied to omega of x0, and when you throw out xi and have xn, this would be wonderful. This would be the wonderful formula, right? You throw out xi and you evaluate omega on these things, but then evaluate xi on these things. This would be a beautiful formula. This formula is, of course, completely wrong. But the first thing you notice, it should be alternating for some reason. So this is the correct sign. This I happen to know.
Should we have to G?
Who's speaking? Yes?
Xn instead of x.
Oh, I put n here. I'm sorry. Yeah, thank you. Up to. Yeah. Go. Yeah. So you kick out xi, and then you hit the result with xi. But to get, you see, it's pretty obvious. It has to be alternating because this thing's alternating somehow in here. This is, of course, also wrong. Minus. And now after you've thought about it for a while, actually, every term here makes sense. But I mean, it takes you a while to think about it. You have to evaluate on the bracket. So what you have here is, and now the sign I happen to know, is I plus j here. And you put the bracket at first. You see, you bring everything to the front. This is Lichnerowitz. He's wonderful. Lichnerowitz probably proved this for me. I don't know. And you see, you bring everything to the front. So you've alternated I plus j times. You go here and you kick out xi. Then you go on and then you kick out xj, and then you ended up with xk, and that's the formula. So this is a beautiful formula. It makes sense somehow if you look at it for a few days. Yeah, you need to look at something for a few days.
A few Plutonian days.
I didn't say what. I didn't define a day.
Can you please explain what a vector field acting on a form means?
Please say again.
What is a vector field acting on the form? Can you please?
I don't know what you mean in this context. I'm evaluating the form of the vector field. So what's your point?
No, you have xi of omega of something.
Oh, no, that's a function. See, thank you for the question. Xi is acting as a derivation on this. This is a function. Because I've evaluated a k form on k vector fields.
Okay.
Let me emphasize that. It's very, very nice that you mentioned that. This is a function. Okay? Okay? This is a formula. Now, if you can prove, and you can, it's not so bad that this definition and this definition are the same, right? That's the way you prove that this definition is well defined, because this is obviously well defined, right? Furthermore, it's not so obvious here, maybe the Leibniz rule is correct. But in this definition, Leibniz rule is obviously correct. So it's very capitalistic. You pay your money and take your choice what you want to define and what you get from it. And I chose Cartan formula as a definition. And very quickly I had both properties, namely Leibniz rule and the well-defined. So anyway, this is the main formula. Now, here we go. Note that f, I don't know how much patience or time we have, FGH is certainly up to a sine. Well, that's xf. I know, now I know the sign. And, no, I don't know the sign, I've forgotten it. Minus. Okay. All right. So GH, if I turn it around, I get it right. So this is XG, XH. Right? So F is the differential operator with plus sign now.
The minus.
Huh?
You missed the minus there.
I reversed. No. Thanks. I thought I reversed. Okay. Sorry, thanks. Okay? Right? So F is the XF is the differential operator without a minus sign, but then you have to reverse the order. Okay, so you see here that this is going to be the first terms of this sequence. You see? So what you start writing down in here is so let me just write it. X, F1, three functions, X, F2, X, F3 is, now I'll do it right maybe, X, F1, omega, X, F, now I have to reverse to get it right, Fx3, I'll do it the right way, F minus sign, Fx2, X3. Fx, what? 3. Okay? So up to, this will be a minus sign. And okay, so actually the signs will be shifted by 1 in this term. So you're going to get, you see, and these are the things that are going to appear in the Jacobi identity, is all three things will appear. All of these three things will appear here.
But Professor,
Yes.
you define the brackets to a smooth function. How do you define it to the bracket?
Yeah, you're absolutely right. Yeah, right? Okay, so all three terms will appear in the Jacobi identity, and they will appear correctly here. They will appear, you will find the Jacobi identity here. This will be Jacobi. So the three terms of the Jacobi, and guess what you're going to have here? Exactly this same three terms. So you're going to get Jacobi plus Jacobi equals 0. You see what I'm saying? No. Yeah? So Jacobi, there it is up above. F, well, it'll be down here. So I'll put it on one side. F1, F2, F3. Now I'll bring this on the other side. Minus F1, F2, F3. Minus F2, F1, F3. All right? And you see, the first thing you're going to get is this thing. The second thing you're going to get, so you need to turn this around, and you'll get F3 with a plus sign, F3, F1, F2. The next thing you're going to turn this around, you get it with a, no, this is, oh, what am I saying? Yeah, turn this around, and you will find exactly, you will have two pluses and one minus, I guess, and this will be exactly this thing that you have here, and here you will have exactly the same thing. You see, and the key thing is here, because don't forget, so omega of x, F1, x, F2, x, F3, that's what's going to appear here, order of magnitude, is what? This is, well, here it is. It is, what did I say? It's the bracket. So what's the statement of the lemma? Is it there? X of the bracket. So this is x, this is the bracket. So this is omega of x bracket F1, F2, X, F3. And we know that that's the bracket of F1, F2, F3. So you see, terms here will be the same if you check the signs. They don't cancel, you get 2 times the same thing. Yeah? They add up. And that says that the left-hand side of this thing is 0, and that's exactly the Jacobi identity. So exactly as I was saying, the fact that this is a Poisson algebra is this formal computation plus, in fact, the fact that d omega is 0. And the incredible thing is, if you look, I was talking to some French mathematicians who know the collected works of Lagrange. And if you look in Lagrange, you will see that Lagrange understood this in some completely complicated language, in context about the motion of Saturn or some incredibly complicated applied problem. You will see that he understood this fact and understood this fact, that this was the key fact. Unfortunately, the definition of a differential form was not clarified until after the Second World War. Yeah, very interesting, right? Very interesting. My Japanese friends tell me Chevalier came to Japan and explained to the Japanese mathematicians after the World War exactly what a differential form should be, and it opened their eyes like this. That's not so long ago. You all were not born. Nobody here was born except for me. But that's not so long ago. And Lagrange and all of these great mathematicians understood the stuff, but did not have it really formalized in a nice way that we have it here. This very simple statement. All I do today is the basic sequence of symplectic geometry is a sequence of Lie algebras. Okay? So see you.